Well, thank you very much for the invitation. Really, really excited about this. I've got a lot to say, so I'm going to go and get straight to the point. I'm going to give you a sort of brief personal history of the links between AI and neuroscience, how brain has been a source of inspiration for AI, particularly with artificial neurons, but also feed-forward architectures for recognition and categorization, which has been one of my main things, spike-based coding, and at the end, I'm going to talk about my current project, possibly my last ever project, which is TerraBrain. It's building trillion neuron systems that can run on standard hardware. And I'm going to show you a simulation with 86 billion neurons running on my Mac. So anyway, quick potted history. Everybody knows, what McCulloch and Pitts back in 1943, Alan Turing, Rosenblatt. And then you got Minsky and Papert basically sort of killed everything off by proving that perceptrons can't do exclusive OR problems. And that led to the first neuro AI winter. Now, I started my thesis in 77. I was recording neurons in Edmund Rolls's lab, finding neurons that responded bimodal responses to food, bananas, taste and sight of a banana. And I wanted to find some models to how to do this. And there was simply nothing. I mean, really, I looked in the literature, there's nothing happening. It was dead. There were people like Fukushima, is one of the first people that I could find. But then things really picked up at the start of the 80s. You got Hopfield and McClellan Rumelhart, Jeff Hinton and Lecan with black propagation, Terry Sishnovsky, and things were looking really good. I thought, we're going to solve all this. And then, well, at least from my point of view, early 90s, I used to go to things like NIPS, and I couldn't understand anything because it was all this maths and sort of support vector machines and things like this. And for me, people weren't talking about the brain anymore. It was very difficult to make the links. At least for me, it was like another second neuro AI winter. Things started to change when Fei-Fei Li came up with ImageNet in 2009, because 3 years later, Jeff Hinton and his two students had absolutely demolished computer vision with their paper, which has now been cited more than 173,000 times, with a really, really dumb feed-forward architecture that completely wiped the floor with conventional computer vision. And, this is, I don't have a pointer. Anyway, never mind. So 2012, that was the first green dot is the first of the deep learning systems. Humans could do slightly better at the time. And so the year after that, humans still had a chance. But basically, by 2015, the systems were getting above superhuman performances. So, and things didn't stop then. 2017, Google Research got the transformer model, and that's the basis of all these large language models. And people are talking about artificial general intelligence now and super intelligence and so on. So my contributions in this, well, it turns out that in 1989, I wrote a paper where I basically said, on the basis of the latencies of neurons in the visual system, that it had to be basically a feed-forward pass to be able to do things like face processing. And I backed that up with my biggest hit, which is a paper in Nature in 1996, where we showed if you flash an image that the subject has never seen before for 20 milliseconds, they can very, very rapidly and very efficiently decide whether there's an animal present. And this led to the idea that this is a figure that gets used a lot, where an image going through the monkey visual system in 100 milliseconds, to make face selective cells in IT, you don't have any options but a feed-forward pass. We did a lot of stuff on what I call ultra-rapid visual categorization with my students, one of whom was Rufen van Rulen, who after his thesis, he went to Caltech and was working with Christoph Koch and Pietro Perona, and had a very bright young student called Fei-Fei Li working with him. And they showed that you could do animal categorization without any attention at all. And so when Fei-Fei Li got a job at Princeton and decided to set up ImageNet, everybody thought she was completely mad, but she didn't, because she knew that humans could do this sort of categorization task extremely efficiently, and therefore ImageNet was, I think it's fair to say that it was designed to test that ability to do categorization. And so there's a sort of, there's a link from the work on the brain on fast visual processing, ultra rapid visual categorization, right the way through to ImageNet and then AlexNet and all the rest of it. So you could say, well, that's okay. We've learned enough about the brain for all that. Is there anything else? I mean, can AI just continue to go forward, getting even more and more sophisticated without knowing any more about brain mechanisms? I'm going to try and convince you that the answer is very definitely no. Now, classical neural networks, the ones that you find everywhere in AlexNet transformers and so on, have the activations. I mean, here we've got a neuron. No, I normally would have a mouse. Anyway, no, it doesn't matter. With everything's coded in floating point numbers, the weights, you final activation, you sort of multiply everything together, then you put it through some output function. These are all expensive computations. So, even with 6 inputs to the neuron, 16 inputs, you've got a lot of compute to do. So this is very expensive, and it gives you an energy problem, which is that if you wanted to simulate the human brain in this way, quick back of the envelope calculation, 86 billion neurons, let's assume 7,000 each, because as we were saying yesterday, I mean, in the cerebellum, you can get hundreds of thousands of synapses on some neurons. And if you wanted to recalculate everything every millisecond, you would need 600 petaflops. Now, if you take the super computers on the planet, there are 3 that can do that currently. They're all in the States, and they all use over 20 megawatts. We've got the Jupiter Exascale computer in Jülich, the European Supercomputer Center, and that will do it as well. I'm not sure whether it's quite on stream yet, but it's using 18 megawatts, so it's better than 20 megawatts. But this is 1 million times more inefficient than the human brain. Do not try and use the exascale thing to simulate the human brain. It would be insanity. So what's the secret of the brain's 20 watts? Well, a lot of people here think it's neuromorphic computing, and I think, I'd agree with you on that. It could be that it's, we're using analog computations. Jeff Hinton gives talks where he says that's the secret. We're using things like memristors, and this is very power efficient relative to conventional computing. But I'm going to argue and try and convince you that the real thing is using spikes, not floating point numbers. Now, everybody knows that brains use spikes, but 99% of the research, he says, roughly, assumes that it's the firing rate that counts. And you can measure the firing rate in various ways. I mean, it could be the number of spikes in a fixed time. It can be the interspike interval. We heard about that yesterday. The worst possible way to send a rate code is as a Poisson code. It's absolutely disastrously inefficient. Personally, I think all of these are really bad, because there's a perfectly good alternative, temporal coding. It's where you process information with a wave of spikes. You use the fact that the most activated neurons will tend to fire first, and that allows you to code information in the order of firing of neurons, even with only 1 spike per neuron, for a very simple reason that if you think of a retinal ganglion cell, if you put in a weak stimulus, it gets to a spike at a longer latency than when you have a strong stimulus. Everybody knows this. And you get these sort of intensity latency functions, which basically are saying that sensory neurons are intensity to delay converters and not the conventional view that the neurons are intensity to rate converters. And the amazing thing is that this was shown in the very, very first paper ever on the physiology of the visual system by Lord Edgar Adrian in 1927 in the Journal of Physiology. He got the Nobel Prize for this sort of thing. It's not as if it was secret. And he was recording from the eel optic nerve, dissecting away the fibers, flashing, turning on lights for 300 milliseconds. And in the paper, there are 2 intensities. And you can see with the higher intensity stimulus, you get higher firing rate, initial firing rate, and higher maintained firing rate. But look, you've got a shorter latency. It's like half. The latency is about half with the higher intensity stimulus. It was in the very first ever study on the visual system. And that fact has been ignored by neurophysiologists and modelers, I think, for decades. So, going back to my potted history of the brain, of the AI and the brain, that paper back in 1989, I also pointed out that because of the speed constraints, you can't measure firing rates. And so I was suggesting that it would be the arrival time. So there's a short 4-page paper I published in a conference in 1990, where I specifically said spike arrival times could be a highly efficient code. And then with my students, we tested this idea. Rufen van Rooyen, Jacques Gauthier, and Arnaud Delon. We had this paper here. This is 1998. This is, you can see this flashing an image of a face. You've got sort of retina and orientation maps. And you can see this wave of spikes going through the system, 1 spike per neuron, but you've got all the information you could possibly want just looking at the order in which the different orientation maps fire. And we decided to set up a company called SpikeNet Technology in 1999, which sort of limped along until 2016 when we were bought out by BrainChip, and they have all the rights to the technology, which they could use in Akida, but they don't. In the early days of SpikeNet, this is between 2000 and 2002, we discovered actually you don't need to use the ordering of activities. I mean, it's way over the top. With 16 different inputs, there are 16 factorial orders. You don't need to decode those. What we do instead is, well, we do the intensity latency conversion, and then we pick off the first N neurons to fire out of M. It's called N of M coding, and it allows you to do lots of fancy things after that. And I'm very pleased to see my friend Steve here, because 2004, he came up with exactly this idea, N of M coding, 2004. I mean, basically great minds think alike, I think, because this is what we discovered. We never published it because it was a secret source, if you like, that kept the people's jobs at SpikeNet Technology. So you basically probably have never heard of this. Anyway, the idea is you can take neurons firing a wave of spikes, put a series of relay cells and a little inhibitory circuit. I'm frustrated. I don't have a mouse. Anyway, doesn't matter. Hopefully you can understand it. And this inhibitory circuit counts the number of spikes that are fired. And when it gets to some value, let's say 4, it blocks anybody else going through. So you can pick off the first 4 spikes. You can also do that right on the input layer. You could have, if the retinal ganglion cells, when they fire, had a little inhibitory circuit, you could do that. I don't think that happens in the retina particularly. It's more in the geniculate where you would do this. The great advantage of doing it on the input is you don't even need the 16 spikes from the input layer. So it's just 4 spikes. So that's how to make power efficient hardware. Now, if you take those 4 spikes coming out through the system and you feed that onto neurons with binary synapses, you've got an extremely selective mechanism. Here we've got 4 neurons with 4 binary synapses, and each one of them is tuned, set up so that it will respond to a particular set of first N. So JKCB makes this first cell fire. It doesn't actually matter what order they fire in. No variable weights. Each output neuron fires to a specific pattern. This other cell likes OMDH. This one wants PLCG, and this one likes KMOA, and so on. So let me just illustrate that you can do something useful with this. I'm going to make a little model face detector with actually 18 inputs. You've got a 3x3 pixel array with 2 orientations at each one. So in this particular pattern of activity, which corresponds, if the first 4 neurons happen to be 2 horizontal lines here, another one here and a vertical, then we actually see a face. I mean, I think it's very difficult to avoid that. And that's precisely what this thing will do with 4 synapses and 4 spikes. That's exactly what we did in SpikeNet's recognition engine, except that rather than being a 3x3 patch, it was a 28x28 patch, and rather than 2 orientations, we had 8. But basically, it's the same thing. And that model basically allows us to produce a detector which is remarkably selective and robust. So imagine we make this. You take a patch of image, you pick out the first firing orientation units, and you set the weights on those things, and then you copy that. sort of convolutional neural networks. It will look for that everywhere in the image. And these little red dots here are where the neurons in that map have gone over threshold. And you can see with the original image in the center, it works fine, but it also works with all these extremely low intensity images or low contrast or blurred images or noisy images or whatever. It works fine because the ordering of firing isn't changed by messing up the contrast. It also, this is one neuron model. It's also orientation and size invariant to a substantial amount, and also can adapt to changes in the viewing angle of a 2D picture. That's all with one-shot model with one training example. Now, we didn't publish this, but there are some papers from back then where you can see that this actually was really working very well. Here we've trained the system to respond to learn the eye of the cat, and it's found 2 of them, which is normal. And it took, in this case, 5.7 milliseconds per model. This is 2004, well, actually before that. And in this other paper, you can see I just made a sort of montage by taking 51 little bits of images. You can see Batman and Bambi and Fleetwood Mac's, anything from the web. Make a model for each of them. It performs perfectly, and finding and detecting and localizing 51 targets in an image that size took 241 milliseconds. This is in 2002, right? I think if you did exactly the same thing, if BrainChip did exactly the same thing today, it would take microseconds probably. So interim conclusion, biology uses spiking neurons, intensity latency conversion, information containing the order of firing, use inhibitory circuits to control the number of neurons that fire, N of M coding, binary synapses, and I think that goes a long way to explaining the remarkable energy efficiency of the brain. So basically, just summarize, conventional processing with floating point numbers, even event-driven, if you've got floating point weights, and then you've got event-driven spike processing with unary synapses, and the ultimate is unary synapses and N of M coding. All of these ones are just very expensive because they've got floating points. These are easy to do because you just have to increment the targets. And you can control the sparsity very easily here. You've got this one-shot learning rule I explained, and it's all unary connections from the N inputs fire. There are no zero weights here. This is zero less computing. Can these ideas be scaled up? Well, that's what we've been testing. Aditya Kar, PhD student in the lab, last year at NICE, I had a poster, and I was stuck in front of my poster for 2 hours running this simulation on my Mac. It was 4 billion neurons, 250 connections per neuron, 1 trillion connections, 8,000 neurons spike on each cycle, so N is 8,000, 3 cycles per second roughly. We didn't get accepted as a paper, so it didn't get published in the proceedings, but if anybody wants to read it, the paper is actually it was put on an open archive, so you can download it anyway. The trouble with that is that it was stuck at 2 to the 32 because of the way the code was written. And Aditya disappeared off. He was doing some other stuff with his other co-supervisors. So I was getting rather frustrated. And so I'd like to show you what I've been doing myself literally in the last 3 weeks. I've got my Super Mac here with 128 gigabytes of RAM. I've got SSD things here. I've got a 4 SSD array under the desk here. And on the 2nd of March, I said, oh, there's a conference coming up. I'm just going to see if I can make the code run above the 4 billion. I completely rewrote the code from scratch with the help, amazing help of Claude Sonnet 3.7. I wouldn't just, if you've not tried writing code with it, it's just unbelievable. I literally said, Claude, I'd like to simulate a very, very large network of extremely sparse spiking neurons using unary weights. Can you help? He said, yes, of course. And he was just generating. It was absolutely astonishing. I've never, ever had a student anywhere near as reactive. So basically, I'd not written anything I've never written a Mac app in my life. This is all done with Xcode and Swift and Metal. And I'm going to show you a simulation. I've got 6 trillion connections. I'm storing all of the connections as a 5 bytes that can address 2 to the 40 different neurons. I'm not using all of those here. It's a true terabrain architecture in the sense that it really will handle a million. And this has been running on battery all the time I've been giving my talk. And I can put here, I've got the number of the red dots are neurons which are getting excited by the yellow dots are the neurons that spike. The red dots are the neurons that are being updated because they're on the list of targets. And I can, in real time, I can play around with the number of connections per neuron. And I'm using this N of M thing, which Steve and I love, because unlike a conventional spiking neural network with fixed thresholds, where if you start with 1,000 spikes, either the system dies or it has an epileptic fit. The N of M trick allows the system to keep running all the way through my talk with exactly the same number of spikes per thing. And just it's quite fun. Whoops, sorry. Maybe I'll just stop this. You can see this is just picking out a neuron and looking at all its what it's projecting to. So I mean, it's really, really dumb. I wrote this code in less than 3 weeks, not being able to write a Mac app. Okay. Conclusions. That's today. By the way, when I managed to show that it makes no difference how big the network is, I went up to actually 100 billion neurons, and Claude, we did all the benchmarking, and this is what Claude said: "What an incredible achievement! You've successfully run a benchmark that proved your terabrain system can scale to 100 billion neurons, etc." And it's true. And the reason why that's the case is because we never do anything to all the neurons, except we just look at the things that get updated. So I've already ordered a Mac Studio, the Mac M3 Ultra. It's got 512 gigabytes of RAM and 6 Thunderbolt 5 interfaces, each of which will be do 80 gigabits a second. My plan is to not just this is all just meaningless because it was just propagating random spikes. But I want to build a system like this where you have images coming in at the bottom and your outputs up here, and you've got a sort of episodic memory sort of thing where so every time a new pattern comes in, you store it as an episodic memory trace, and so on. And then you can sort of activate things in this episodic memory trace and reconstruct what you expect to happen. And that's going to happen real soon now, at least with a bit of help from Claude. I think this could be really soon. Right, so just in the last minute, let me just point out that this sort of architecture, if you try to do it with memristors, you would need, quintillion devices. So, yeah, you could do. I think I'll stop. The point is, there are neuromorphic systems which will do brain scale computing, spin cloud, there's deep south. They're still using a lot of energy. And I think one of the reasons for that is because people believe that every neuron in the brain is firing one or two spikes per second. And therefore, 86 billion neurons, you need to process 86 billion spikes per second. I don't believe it. It's one of the things I've been pushing for a long time is the brain is actually a lot quieter than we believe. And that is the key to power efficiency. So if you can get down to 1,000 spikes per second, then your energy consumption is as low as you like. And so, just basically the bottom line is that, yes, we've learned a lot from the brain, etc. Spikes in particular are important. And I think it's the secret of the 20 watts power budget. And it drives me crazy when I hear announcements of $500 billion dollars being spent in the States to build these supercomputer centers with 400,000 NVIDIA chips. And in France, it's 109 billion euros which is going to be spent on this. This is insanity. The neuromorphic community has to tell these people to stop it. It's insane. And that's my final comment. Yes.